last time we were discussing the effects of the ionosphere and the troposphere on the GNSS signals. We noted that the signal enters the ionosphere at about 1000 kilometers from the surface of the Earth, and then at about 40 kilometers from the surface of the Earth it enters the troposphere. Ionosphere is a layer of charged particles, basically ions and free electrons. During the daytime, sun's ultraviolet radiation breaks up molecules, oxygen and nitrogen in the lower atmosphere and hydrogen and helium in the upper atmosphere into ions and free electrons. Then the electron density increases rapidly and peaks at around 2 p.m. local time. Okay. So at around 2 p.m. local time of the ionosphere, the electron density becomes maximum and then it starts to fall. Then at night, there is no ultraviolet radiation, so ions and free electrons recombine, and this reduces the electron density further. Now, depending on the electron density, the ionosphere is further divided into 4 sublayers, okay, D, E, F1 and F2, and the electron density also varies in these layers. It is maximum in the F2 sublayer around, for some region of the F2 sublayer around 250 to 400 kilometers. In that region, generally the electron density is maximum. The electron density also shows variability with season. Then depending on latitude and basically latitude, the density varies greatly. Then it also depends on the solar activity. What is solar activity? Solar activity is basically determined by the solar magnetic field. So the electron density shows diurnal variation, meaning variation between day and night, and seasonal variation. It also depends on latitude and the solar activity. Okay. The solar activity is determined by the solar magnetic field. Okay. You may know that the solar magnetic field follows an 11-year cycle. Okay. During this 11-year cycle, the sun is not always active. Okay. So it is characterized by a few years of high activity followed by a few years of low activity. Okay, and also the sun's the polarity of the solar magnetic field reverses every 11 years. Now, during the periods of high activity, high energy radiations in the form of X-rays and giant clouds of charged particles leave the sun and propagate in all directions. So part of this also reaches the Earth and interacts with the Earth's magnetic field. So when such interactions happen, the electron density rapidly builds up in the ionosphere. Okay. And this certainly affects the GNSS signals, because later we'll see that the ionospheric error that we mentioned all these days heavily depends on the electron density of the ionosphere. Okay. So the electron density shows variability with the day and night. It changes about 10 to 100 times between day and night. Okay. It also has seasonal variations, varies with latitude mainly, and the solar activity. Now the troposphere is basically a medium of neutral gaseous molecules. So the behavior of the signal in the troposphere is different from that in the ionosphere. As we discussed, this will be clear to you. But both the layers change the signal propagation speed through refraction. So the signal travels at a different speed from the speed of light in a vacuum while passing through the atmosphere. As a result, the arrival time of the signal changes. So we know that the pseudo range is given by this formula, C into TR minus TT, where TR is the time of reception or receive time and TT is the time of transmission. Now let's write different components of these two times, TR and TT. I'll first write TT. So TT is the transmit time. So this is the true transmit time plus delta T. This is the satellite clock here. Now the satellite clock, the clock on the atomic clock on both the satellite is used to derive this transmit time in the receiver. Okay, now the clock, we know that the clock, even though it is steered by the control segment, has small drips from the GNSS system time, and that error gets added to the time which is done by the satellite in the navigation data. So this is the satellite clock error, which changes the transmit time that the receiver decodes. Then TR has several components. This would be the reception time, this TR true would be the reception time had there been no error, no atmosphere. The signal travels from the satellite to the receiver at the speed of light. Then this would be the true receive time. Okay. Now since we use the receiver clock to find this time, the error of the receiver clock gets added to it. This is the receiver clock error. The signal travels through the atmosphere at different speeds. As a result, the receive time is changed. So let's say this is the extra time that the signal spends in the ionosphere, and this is the extra time that the signal spends in the troposphere. Okay. So these are different components of the receive time. Now if we put all these things here, we will also have some epsilon. That epsilon is basically noise and multipath. Okay, multipath actually affects this TR. Okay, I have not included that here. That's why I have put noise and multipath here in Excel. So if we substitute for TR and TT here using this, we have different components. And we'll take the clock part. This is the clock part. It has both receiver and transmit. So simply saying clock is not sufficient. You need to specify a receiver and transmitter clock, receiver and satellite clock. Then we have C into delta T iono. This is the ionospheric error. And then we have C into delta T tropo. This is tropo error. And then epsilon. So these are all different components of the pseudo range. Of all these, we are actually interested in this, and this can be corrected using the navigation data. Navigation data has information about the satellite clock error, so this is corrected by the receiver by decoding the navigation data. This is an unknown. The receiver wants to estimate this, and then we are actually interested in this part. This is the geometric range or the true range. This one is actually true range. Okay, there are some other sources of error as well, but we'll not consider them here because they are not large errors. They are very small errors. Okay. So this is the true range, and let's denote this R. And this R is actually a function of satellite and user position. The X, Y, and Z components I am writing. Okay, now if we do it for ith satellite, this will be I. X. Okay, now this XS, YS, and ZS are satellite position in the ECF coordinate frame, and from the navigation data we get the ephemeris or the orbital elements of the satellite, and there's a standard algorithm that can convert. So using the orbital elements, we can determine the satellite position in the orbit at a particular time of interest. And then using that standard algorithm, we can convert that position into the ECA. Okay, so XS, YS, and ZS are known from the navigation data. The unknowns are XU, YU, ZU, and the receiver clock error. So you want to estimate these clock errors and the user position. And for that, these are actually nuisance. These are errors, so either we want to eliminate them or we want to partially remove them using some mathematical models. Okay, this is eliminated. This and then user position we want to estimate, and these are actually nuisance for us. We cannot remove this one. We can only statistically model this. Okay, but this cannot be completely removed. Partially removed using model. And this can be depending on what measurements you are considering. This can be completely removed. Of course, the penalty is that added error, but it's possible to remove this, and we'll see how that is possible now. In order to do that, let's first find the ionospheric error, expression of the ionospheric error. I'm just writing iono error, okay? Iono stands for actually ionospheric error. So you are interested in finding this error. We know that the refractive index is given by this. So this is the refractive index. This is speed of light. F1. And this is the propagation speed of this signal. let's say in the ionosphere. Now, the ionosphere acts as a dispersive medium for radio frequencies. What does it mean? It means that N varies with frequencies. Okay, it can be shown that N is given by we are considering the carrier now. Okay, we will find the ionospheric carrier for the carrier. Later we will see the effect on code quickly. So F is the carrier frequency and Ne here is actually electron density. So N is the refractive index, Ne is the electron density at some point. So if you take this at some distance L, then this will be the corresponding electron density at some distance L. Okay. Now what is the travel time of the carrier through the ionosphere? Let's call this T ionode. So we are going from the receiver to satellite. So here is the receiver, here is the satellite. We are interested in this signal path. So let's say at some distance L, we consider an elementary length dl. So how much that time would be for the signal to travel this length dl? It will be dl by v. V is the speed of propagation of the signal. And here I have considered the entire distance between the receiver and the satellite. Now see, there is a particular layer of the atmosphere which contains free electrons. So although we consider the entire length, the electron density would be 0 outside the ionosphere. So whether you integrate it from the beginning of the ionosphere to the end of the ionosphere or from receiver to satellite, you basically get the same thing, because outside the ionosphere electron density becomes 0. Now here we substitute for V. So using this expression we substitute for V. And then we have this one. Next we will substitute for N of L using this expression. Okay. So this is the travel time of the signal through the ionosphere. So had there been no ionosphere, what would have been the travel time? The travel time in a vacuum is, let's call the T dash. Then the signal would have propagated at the speed of light, right? So V would have been C. Right? So this would have been the travel time in a vacuum. So what is the extra travel time? And that is the ionospheric error. This is only delta T I know that we wrote in the expression of pseudo range measurements. We need to subtract this one from this. Now see here we already have this term, right? So after subtraction we basically have the second term. So I am eliminating the first term because it cancels when we subtract this one, and we just have this one, the second term. Right? So taking this 40.3 outside, and then the carrier frequency will be the same for a given signal. So we can take the carrier frequency also outside, and we have this integration. Any of L is the electron density at distance L from the receiver. So this is the receiver, this is the satellite. We connect the two, and this is the signal path. So we calculate the distance from the receiver. So any of L is the electron density at some length L from the receiver, and dl is the elemental length. Now this integration actually integrates the electron density from the receiver to the satellite, right, with respect to the path length. It is called total electron content. Take. What exactly is this? This is the number of electrons in a tube of 1 meter square cross section. So you are actually integrating the density with respect to length. Okay, so we will get the total number of electrons only if we consider the cross section of 1 meter square. So total electron content is the number of electrons in a tube of 1 meter's cross section extending from the receiver to the satellite. So just consider a tube extending from the receiver to satellite of 1 meter square cross section. And how many electrons are contained by this tube? That is the total electron content. Okay. So T INO is given by 40.3 CF carrier square times TEC, total electron content. But this is an unknown, and that's why delta T INO is an unknown. And there is a negative sign here. What does the negative sign indicate? And why do you have a negative sign? Because the refractive index of the carrier in the ionosphere is less than 1. So this indicates that V, which is in the denominator, is more than C. Okay. So the carrier travels at a speed higher than the speed of light in a vacuum. This is why the refractive index is less than 1 for the carrier, and as a result delta T INO is negative. The carrier travels faster than light. Okay. How about code? Now, from the signal structure, we know that the code modulates the carrier. For the simple signal structure that you have considered, the code just modifies the amplitude of the carrier, right? So it can be shown that for the modulating waveform, the refractive index is given by this. Using math, it can be shown, but we will not get into that. The same as carrier, only difference is it is plus. Okay. And this frequency is not the frequency of the code. It is the frequency of the carrier, okay, which the code modulates. So in this case, the code is the modulating waveform, which modulates the carrier. So in case of the code, the refractive index is greater than 1, meaning the speed of propagation is less than the speed of light in a vacuum. So code and carrier travel at different speeds through the ionosphere. They do not travel at the same speed. Okay. So for the code, we can do the same thing as the carrier. The only difference is that instead of negative here, we will have positive, right? So everything will remain the same. Only difference is that instead of negative here, we will just have positive. So here I'll write carrier because this is for the carrier. So following the same approach as before, This is what we get for the code. So the code travels slower than light in the ionosphere. So 45.3 is a constant. Carrier frequency is known. The only unknown here is the take. C is also there. Speed of light in a vacuum, C is there. C is also known to us. Only unknown is this one. Right? Now let's write this whole thing as A by F square. 40.3 and C is multiplied to take and written as A. Okay. And here we wrote the expression for pseudo range. The pseudo range is actually derived from code. When we talk about the receiver operating principles, from tomorrow we'll start the discussion of the receiver operating principles. There you will get to know why the signal has been intelligently designed this way, how we can find the pseudo range measurement using the navigation data and code. Okay. It is also possible to derive an equivalent distance using the carrier. That will be more precise, but we will not get into that. As far as this class is concerned, we will talk only about the pseudo range measurement derived from the code. So this one here, this one is actually the ionospheric error for code. Okay. And we have seen that the ionospheric error is inversely proportional to the carrier frequency. This is true for both carrier and code. The only difference in case of the carrier is that you need to put a negative sign. So when you write the equivalent expression for the carrier, in that equation instead of putting plus, you have to put minus for the iono part. But since we have considered only the code here, pseudo range measurements are derived from the code. We will consider only the positive ionospheric error here. The ionospheric error is inversely proportional to the square of the carrier frequency. Now we can use this fact to eliminate the ionospheric error. How we can eliminate the ionospheric error? If we can determine A somehow, we can eliminate the ionospheric error. And why do you want to eliminate the ionospheric error? Because it is the dominant source of error. If we can eliminate the ionospheric error, we can improve the positioning accuracy to a great extent. So you would like to eliminate the ionospheric error. It is possible because the ionospheric error is inversely proportional to this term. It is possible to eliminate it using the dual frequency measurements. So let's consider the pseudo range measurement. of the same satellite in two different carrier frequencies. We know that GPS has three carrier signals, L1, L2 and L5. INSS has two. New satellites will have three carrier signals. Okay. So let's consider L1 and L2. We can pick other frequencies also for GPS, L1 and L2. In case of IRNSS, you need to do L5 and S here. So we want to write the expressions of the pseudo range measurements, dual frequency, two frequencies, two carrier frequencies we have considered. Okay. So in this case, see, pseudo range is derived from the code. In this case, the code modulates the carrier in the L1 band. For this case, the code modulates the carrier in the L2 band. That's why I put L1 and L2. So the F carrier in the denominator will be different for the ionospheric error because the carrier frequency is different. Now we want to write the expression here. We know that we have the true range. So I'll write Ri. Now since both are coming from the same satellite, Ri will be the same for both. We know that the ionospheric error is different because this one will be FL1 square and this one will have FL2 square. How about this AI? A actually, so we have 40.3 and C, they do not depend on the carrier. How about the take? Total electron content? By definition, total electron content is the number of electrons in this tube of 1 meter square cross section. That also does not depend on the carrier, right? So A will be the same in both, right? Now how about the other sources of error? We know that in the pseudo range measurement equation we have other sources of error. Now see, clock. Satellite clock will be the same because both measurements are from the same satellite. Receiver clock will also be the same because we are using the same receiver clock for both measurements, right? So this is different. Later we will see that the tropospheric error will be the same. We'll see that it does not depend on the carrier frequency. So this also remains the same. Epsilon, which is noise and multipath, will not be the same. Epsilon will be different, but epsilon is statistically modeled. Okay, so in our subsequent discussion, to find the ionospheric error, we'll ignore this epsilon. We do not know epsilon. Okay, we'll ignore this epsilon and then determine AI. The downside of ignoring epsilon is that epsilon will affect the calculation of AI. Okay, and it will introduce some error. It can be shown that epsilon, after finding AI, epsilon actually increases. But that is the penalty that we pay. We have no other option. We do not do epsilon. So we have to ignore it. Okay. So here, if we ignore epsilon, we see that all other error sources remain the same for both the measurements. The only difference is this one, ionospheric error. So all other error sources we can write as, let's say, theta, and I'll write ignoring epsilon. So here though, if we subtract these two, so let's say if you subtract L2 measurement from L1, this will cancel. Theta will also cancel. We are ignoring epsilon, so we will not consider epsilon anymore. Theta cancels, R cancels. So only difference is caused by this term, right? So by taking the difference between the two measurements, and rearranging the terms. AI is given as follows. I'm not showing the intermediate steps. You can do it. It is straightforward. I'm just subtracting this one from this. And rearranging the terms. That's all. Okay, so we found AI. Next, what we can do? We can put this here, right? And then subtract this term from this pseudo range. The resulting term will not have INO error. The downside of this that epsilon would be increased. Okay. Similarly, from this one, if we subtract this, substituting for AI, we get the pseudo range for L2 without the INO error, and its epsilon will also be increased. Okay. So this is how, using the dual frequency measurements, it is possible to eliminate the ionospheric error. But how about the users that do not use dual frequency measurements? If the user can process only single frequency measurements, if he has a cheap receiver which does not process dual frequency measurements, what will the user do? The single frequency users various models have been ionospheric models. Have been developed. So what they do is they predict the ionospheric error using this mathematical model, and whatever the model outputs, that is subtracted from this. So this partially removes the ionospheric error. Depending on the model, it may or may not remove a bulk portion of the ionospheric error. Okay. Some of the models are as follows. The Klobuchar model removes, this was the oldest model, about 50% of the actual errors. Okay, it is an empirical model. Obtained by fitting INO errors over the US region. Okay, by fitting the INO error over the US region, some model coefficients have been obtained. Okay, and these model coefficients are broadcast by the satellites in navigation data. So they are called Klobuchar model coefficients. Okay. Another model is called SBUS, satellite-based augmentation system. We briefly talked about SBUS while discussing different types of GNSS systems. GNSS grid-based model. Okay, this model was first introduced in SBUS satellites. So SBUS has some geostationary satellites, one or two geostationary satellites, typically two geostationary satellites that transmit additional connection. So this model was first introduced in SBUS satellites. Later, newer constellations and newer signals have adopted this. Okay, for example, IRNSS also transmits a grid-based equivalent grid-based model for the Indian region. So in this case, what happens? The entire world map is divided into a number of grids, and that's why we call it a grid-based model. Okay, and the satellites transmits the ionospheric errors at these corner grid points with some bound. Okay, we also provide a statistical bound. Like 1 sigma bound is provided. Okay, and then the user finds in which cell it is. For example, let's say it finds that it is in this cell. So each corner grid point has corresponding latitude and longitude. The entire world map is divided into these grids. So a user anywhere in the world can find that he or she is in some grid. So the first thing that the user has to do is to find in which cell he or she is, and then he knows the errors at the corner grid points, right? He or she can find the ionospheric error at his or her position using these corner grid point iono errors and some interpolation techniques. Okay, so using a suitable interpolation techniques, it's possible to find the ionospheric error from these corner grid points within the grid. Okay. Then another model which was developed for Galileo is called Galileo-Nequac model. Now in this case, what happens? This is a highly precise model, okay, highly accurate, much more accurate than the Klobuchar model. So using the Galileo-Nequac model, what is done is that along the signal path, the electron density is calculated. Okay, it is divided into a number of regions, and the electron densities are calculated at different regions using diurnal variation, day to night variation, seasonal variations. They also take into account longitude and latitude and the solar activity. So all the different variabilities are taken into account, and along the signal path, the electron densities are calculated based on all these different factors. And then they numerically integrate the electron densities from the receiver to satellite and find the total electron content. Models the electron density considering all variabilities. And then numerically integrates okay, so naturally it is much more accurate than the Klobuchar model. Grid-based model is also more accurate because the satellites transmit the ionospheric errors at different grid locations, and this can be updated by the control segment and uploaded to the satellites. So both the models, the S-bus grid-based and equic model, are much more accurate than the Klobuchar model. But Klobuchar is a very simple model. Okay? So that's all about the ionospheric error. Next one is the tropospheric error. Now the troposphere will not be able to complete this today. We'll continue tomorrow, but we don't have much to discuss under the tropospheric error, so we'll quickly complete this tomorrow and then move on to the receiver operating principles. The troposphere is composed of dry gases that exist up to hundreds of kilometers, but generally above 40 kilometers or so, the tropospheric error is negligible. Okay? Maximum 80 kilometers. After that, we do not get any significant tropospheric error. And water vapor. Water vapor exists between generally 4 and 12 kilometers. Okay. Now, since we do not have any charged particles or free ions here, the troposphere is non-dispersive, unlike the ionosphere. I'll quickly note the implications of this and stop. Okay. So, unlike the ionosphere, the troposphere is non-dispersive. So, what does it imply? Both code and carrier slow down while traveling through the troposphere, and they travel at the same speed. We cannot use dual frequency measurements to remove the tropospheric error. Okay. So tomorrow we'll quickly see the expression of the tropospheric error, and then we'll do some comparison between the effects of ionosphere and troposphere on the GNSS signal. So that will conclude the discussion of the effects of the atmosphere on the GNSS signals as far as this class is considered. This class is concerned. Um, and then we'll move on to the receiver operating principles. Any question? Fine. You can leave now.
Thank you.